Waves are not made of moving stuff, it's made of moving energy. Have you ever looked at the ocean? Have you ever looked at waves coming in? These waves in the water don't carry water from far out from sea. They don't carry that to shore. It's actually the same water, it just moves up and down when this energy travels through them. Waves are simply a disturbance in the medium. What moves forward is not the particles of water. The particles don't go along with it, they move up and down. The waves are simply bringing energy and shape. What travels forward is the shape. Imagine if you had a rope and you tied it to a fence post and you hold it at one end. You give it a little flick up and down, and a pulse is sent to the end like this. This pulse will travel until it hits that fence post. So it will move along till it hits the fence post. And your wave did move forward when you flick the rope. But the rope itself did not move forward. It's in the same position. So when you throw a rock into water, the water will ripple, but the water doesn't move. Before we look at the types of waves, their speed, and how to solve wave problems, here's some stuff that you should know. There's two types of velocities when it comes to wave. First is the wave velocity. Second is the particle velocity. There's a difference. The wave velocity is how fast this disturbance moves forward. For example, on the rope, how fast was your pulse traveling to the end? Particle velocity is how fast the individual points move up and down. It's not the same, and it's not in the same direction. The second thing you should know is that mechanical waves are energy transfers. Sound waves carry vibrations through air. Water waves from the ocean carry motion through the water. Neither carries particles forward. It's just that when the wave energy comes through, the particles shake up and down in that pattern. Last thing that you should know is this wave equation. Wave speed is equal to frequency times wavelength. This symbol. What's wavelength? Wavelength is the distance between crest. So let's say this is your wave. The distance between the highest points is your wavelength. Or you could also do it from the lowest points. This is on the free cheat sheet in the description. And so the big picture is that waves are like messages. The medium stays, but the message travels through. Moving on to the types of waves you'll see and speed. Why do sound waves hit your ears instantly, but a wave moving across a string takes time? It depends on the type of wave. The first type of wave is what we've been looking at, called transversal waves. Motion is perpendicular to direction. For example, look at this. That's a transverse wave. The second type of wave is spelled like this, a longitudinal wave. So unlike transverse waves where the wave is perpendicular to the direction it's actually traveling in, longitudinal waves are parallel to the direction of the wave. How would you graph that? Well, it's graphed like a slinky. You graph the points of density. So some parts are more compressed, and then some parts are less dense. There's examples like sound or compression in a spring. The same equation applies to both. The equation we looked at, wave speed equals frequency times wavelength. Now, what affects the speed of a wave? Transverse waves on a string have a special equation. Velocity equals square root tension divided by this, which is mass per length. So almost like the density, you could say. This is also on the free cheat sheet in the description, and we're going to use it to solve problems soon. But what this equation tells us is that the higher the tension is in the string, the faster your wave is going to move forward. The heavier your string is, the slower the wave is going to move forward because of inertia. So more tension, the particles get pulled back harder, which means a faster response. Here's a practice problem we're going to go through. There's an electric fence wire, and it's taut. Taut means it's tight, like it's being pulled properly. So when you push down on it, it's not just going to flop. It's 500 meters long and weighs 10 kilo. There's 1,200 newtons of tension on this wire. A technician sends a pulse down the wire, and the wavelength of this pulse is 0.6 meters. We're going to solve for two things, the speed and the frequency. Every formula we're going to use to solve this problem is on the free cheat sheet. So first, velocity equals tension over this thing. which is the formula we were just looking at. We can plug in our values here. 1,200 newtons for tension. And the mass per length, which is given in kilograms per meters, is mass 10 kilos over length 500 meters. This gives us 0.02 kilograms per meter. The answer is 245 meters per second. So that's how fast this pulse is traveling down this wire. Next, we're going to solve for the frequency. So look at the wave speed formula, the normal one. We can isolate F with our rearranging skills to get frequency as velocity divided by wavelength. We know the velocity we just found is 245, and the wavelength is 0.6 meters. This is equal to roughly 408 hertz. Great job, we solved the problem. Here's some special things about longitudinal wave speed before we do the next problem. Now, longitudinal waves are just more complicated and have harder math than transversal waves. But here's some formulas if you're interested. We're not going to be using them. In solids, the longitudinal wave speed is given by the elastic force factor over the inertia factor. So this is the elastic modulus, aka stiffness, and this is density. In fluids or gases like oxygen and water, the longitudinal wave speed traveling through is given by the bulk modulus, so the resistance to compression, divided by the density. This is useful if you're interested in engineering topics. Here's a last example problem. A submarine underwater. So that pretty nice submarine. It sends a sonar pulse to the seafloor to detect the terrain pattern. The speed of sound in water is roughly 1.5 times 10 to the power 3 meters per second. And the frequency of our sonar ping, 80 kilohertz. Solve for two values, the wave length, and if it reflects off the seafloor 200 meters down, what is the time it takes to return? Solve this one by one. Look at the wave speed formula. We can isolate wavelength by dividing both sides by frequency. The velocity is the speed of sound underwater, and the frequency is 80 kilohertz, so we multiply it by 10 to the power 3. You don't need to know this. This is more like a unit knowledge thing. The ability to solve is more important. This is equal to 18.75 millimeters. So that's the wavelength, the distance between the peaks. How about the time delay from when you send it down to when it bounces back up to your submarine? The time delay lets you calculate the exact distance to different objects. It's how radars work, and it's how whales use echolocation. It's why they make those big sounds, and then they can tell how deep underwater they are. The total distance down and then back up is 400 meters. And since time is given by distance divided by speed, the distance, 400 meters, divided by speed, which is 1,500 meters per second, equals 0.267 seconds. That's pretty fast. So to wrap it up, here's the key takeaways. A higher frequency means shorter wavelength. A time delay gives precise range info, and it's how medical ultrasounds are done. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.